Hi everyone. So this again is an extension of the fan cart lab. I'm gonna show you if you're having trouble finding the relationships between the force and the acceleration, and or rather the acceleration and the force, as well as the acceleration and the mass. Um, One of those situations, it should be pretty apparent what the relationship is. Another one is going to be a little more tricky as to what the relationship is. And so I want to show you how to linearize data to get a better sense of what that relationship is. So we've seen before how we can use things like Excel to see whether or not it's a quadratic relationship or an inverse relationship and things like that. But what I want to show you today is how you can use linearization to find out what the relationship is between two objects. And this is more of what you're probably going to see on the AP exam, because you may not necessarily have something like Google Sheets or something like that to figure out what the relationship is between two objects, and you can use this linearization technique to find that out. Okay. Now, so again, so now I'm really going to spoil things in this video. What I recommend that you do is that you got, again, two graphs, because you're finding two independent variables with the same dependent variable, the dependent variable being acceleration. One of them you're graphing acceleration versus force. My opinion is that's going to be pretty straightforward. The other one is going to be graphing acceleration versus mass. That's going to be a little more tricky, where you're going to have to use some of these techniques of linearization in order to find out what that relationship is. Now, I'm not going to show you directly what that relationship is. I'm going to use a previous lab that we've done in order to show you these techniques of linearization. This lab I modified a little bit from what we did, in that I decided to make the puck. So I decided to make it so that time of 0 is right when the puck is let go. So now the puck is at rest. It's at 0 centimeters. And then as we go, every 0.05 seconds, I marked the position. And this is the data that I got there. So what that data looks like, I got it also on Google Sheets. And it's right here. So here's the data here. I got the time in seconds and the position in centimeters, like that. And what I'm hoping here is you guys already know the acceleration of this puck as it goes down. I didn't change any of those parameters. So with that, we're going to find out what the acceleration is using this idea of linearization. So I got the position and time data here. I'm going to keep it in centimeters. It's not conventional. Typically you want to convert to meters, but whatever. So, and then I'm going to graph this and just get a sense of what this graph might look like. So if I graph this, ugh, yuck, gross. There we go, that's better. Scatter plot, position versus time, this is exactly what I want. And I can see this graph doing this, and I can go, you know what? That looks to me like a quadratic function. Now, what I've shown you before is you can use Google Sheets to see if it's a quadratic function and see what that fit looks like. However, on the AP exam, you might not have access to as high, as fancy of technology, right? So you could say, okay, this looks like a quadratic, and so that starts at position 0 and starts at rest, right? Because again, if I go back to this video really quickly, right? If I go back to the video, boom, right? It starts at rest. The puck starts at rest. In your guys' lab, I did on purpose, I did not start it at rest. But in this one I'm doing right now, I've set my axes so that the puck is at position 0 and it's at rest when time equals 0. So if I do that, the position is 0. So using this equation, this is beta right here. I call it beta. That's just all. That's what I call the equation. So this is going to be 0 because it starts at position 0, and it also starts at velocity 0. So basically I get this graph of the position is equal to 1/2 times the acceleration times the time squared. So here now is my mathematical model of how the position of the puck is going to change as a function of time, where the acceleration is going to be a constant, time is the independent variable, and position is the dependent variable. So if this is the case, I could see, oh, this should fit a quadratic function. So, and let's go back to the graph, and I see again, okay, that does look like a quadratic function. So my idea right now is that, oh, this position graph is fitting a quadratic function. The way I often look at this is similar to, let's do this. So this is similar to y equals mx, where here is y, so it's fitting the general formula of y equals mx. That's y. Here's x, right? And then in between here, this m is 1/2 times a. M is 1/2 times a. This is kind of the analogy that I'm making here. So in other words, what I'm going to try to do is graph, instead of x versus t, instead of the position versus time, I'm going to graph x versus t squared, with the idea that if I graph x, which is this, versus t squared, which is this, I'm going to get a linear graph. And if I get a linear graph, I can be more convinced that that this function is modeling this relationship. All right, let's see if I can do that. Here we go. So instead of, so again, I'm going to take this, just kind of throw it aside. Take this, throw it aside. And instead of time, I'm going to have time squared in seconds squared. That's going to be my new thing here. But then position I'm not changing, right? Position I'm not changing. So if I look at my model, the position x is the same thing as y. I'm just changing it with, x to y. And this is your general form, y equals mx plus b, but b is equal to 0 in this case. So that's kind of the idea that I'm doing here. However, x is being replaced by t squared. So by t squared. So all right. So instead of time, this is going to be time squared. So I'm going to say equals a2 to the power of 2. And I can do that for all of them, just like that. And then I'll graph this. And the idea is, if I get a linear graph, I can be more convinced that, that's looking good. All right. Let's see what the best fit line looks like. So I make a trend line. Use equation, r squared equals 1. Wow, right? And then my graph equals 182. My graph equals 182. But remember, so this is y equals 182, so that's m times x. And then here's my b, 0.141, negative 0.141. But negative 0, I mean, that's really, really, really close to 0. So I'm just going to ignore that altogether, and I'm going to focus on the 182 times x. So I got now a graph of y equals 182 times x. But again, remember, y is actually my position. 182 is actually 1/2 times my acceleration. And then x is actually t squared. So in other words, 182 is 1/2 times my acceleration. And so if you set those two things equal to each other, 1/2 times the acceleration equals 182, you'll get that the acceleration is equal to, well, twice 182. What the heck is that? 364, about 364 centimeters per second squared, which should be what most of you got for your accelerations back at that ramp lab. Somewhere around there. Somewhere around there. It might not be 100% exact, but it should be somewhere around there. So in other words, this is another way, this idea of linearization is a way that I can graph data and figure out what, if, because the graph of position versus time squared gives me a linear graph, I can be more confident that the relationship here, in this case, for the puck going down the ramp, between position and time, the relationship between position and time is that the position is directly proportional to the square of the time. So that's kind of the relationship that I get out of that. So hopefully that helped. You're going to get more practice as we go throughout this course of linearizing graphs. All right. Bye.